Welcome to the superfast TouchDesigner tutorial series. In this tutorial, we are going to create a blob tracking effect using any video or composition as input. Our goal is to understand how to use the blob track operator inside TouchDesigner to create instances or deformations of the video. I will also explain how the coordinate system provided by the blob operator works. To follow this tutorial, here's what you need to know. 1. Network setup. I'll provide a screenshot of the full network. If it's too large, I'll break it into multiple images with clear indications so you can recreate it without constantly pausing the video. 2. Parameters. Instead of adjusting parameters live, I'll display them as static images, allowing you to copy them at your own pace without interruptions. Let's get started. Chapter 1. Overview. The key concept in this network revolves around one of TouchDesigner's core principles, extracting coordinates from blob tracking to create instances or apply them a text operator. Once you grasp this technique, you'll be able to integrate it in countless ways across your projects. For now, let's focus on mastering this method. It will serve as a solid foundation for more advanced projects. To make this easier to understand, I've set up a simplified network where we'll apply instancing using the positional data from the blob track operator. As a source, I'm using two animated spheres against a solid blue background. The blob track top has two main inputs. The first is the color image, which serves as the main video source, in this case, our animated spheres. The second is the background, a reference frame that helps isolate moving elements. To freeze a reference frame from our source, I've added a cache top, which allows me to pause on a specific frame and use it as the background. This is important because without a static reference, the blob track top would have to analyze the entire image every frame, which is computationally expensive and reduces FPS. By providing a background, the operator only detects differences between the current frame and the reference, making it significantly more efficient. Before we move on, let's visualize how the blob track is detecting blobs in our video. As you can see, the operator identifies and tracks bright, high-contrast areas in real time. The detected blobs are marked with squares, representing points of interest in the image. This tracking happens because the system continuously compares the current frame with the background and detects moving elements. Now, here's my favorite part, extracting and using the tracking data. The blob track top provides all this information inside a table dat, which gives us full flexibility in how we use it. This table contains a set of useful values that help us understand and interact with the detected blobs. First, we have the UV coordinates, which represent the exact position of each blob within the frame. Next, we have width and height, which indicate the size of each detected object. And we have even more data, including the age of the blob, which tells us how long an object has been tracked. All this data allows us to generate instances, whether it's text, shapes, or any other interactive elements, based on the real-time motion of the blobs. Here, I'm using the blob data in two different ways. First, each blob generates an instance at its coordinates. To demonstrate, I've used a simple diamond shape. Second, I'm using the blob ID to create text labels, which are displayed in red to make them stand out. At first glance, this might look simple, but the real challenge comes next. Synchronizing the blob data with instances so they stay perfectly aligned in real time. That's what we'll tackle in the next step. Now, let's apply blob tracking data to create 3D instances. To do this, we need to process the blob tracking data using a series of chop operators that will allow us to manage and manipulate the information effectively. The first step is to convert the tracking data from a table dat into chop channels. To do this, we use a dat to chop operator. Simply drag the table data into the date to chop. Let's review this network for instancing. In this simplified setup, I have a select chop pulling data from the dat to chop, along with two additional select chops extracting specific values. One extracts U and width for the x-axis position and blob width, while the other extracts V and height for the y-axis position and blob height. To handle aspect ratio adjustments, I've added math chops. Right now, we're working in a 1:1 aspect ratio, a perfect square, so no correction is needed. However, when dealing with non-square resolutions, adjusting the aspect ratio becomes crucial. In this case, each math operator applies a multiply operation to account for these differences. Finally, all data is merged here, and a rename operator is added to label the channels properly, making it easier to use them as position coordinates. Let's set up instancing in the geometry comp. Opening the geometry comp VM, you'll see that the blob tracking coordinates are mapped to X and Y. Normally, the first time you do this, it can be quite difficult to find the instances in the camera viewport. This is usually due to the scale settings you're using, as well as the camera settings. Let me show you. I'll select a camera without adjusting any settings. As you can see, the diamond instances are scattered everywhere, except where we want them to be. That's because the camera isn't set up the way we need it to be. To do this, we switch the projection type to orthographic and set the ortho origin to bottom left. The ortho width should remain at 1, while the near value is set to 0.1 and the window size to 1. These values ensure that the camera matches the workspace aspect ratio, preventing instances from being stretched, misaligned, or cut off when resizing the canvas. If you modify the ortho width or window size, you'll notice distortions in the instance placement. This happens because the Blob Track top outputs normalized UV coordinates, where 0U and 0V is at the bottom left and 1U and 1V is at the top right. Using a perspective camera would distort these coordinates, but switching to an orthographic projection removes depth, ensuring a 1-1-1 mapping between blob positions and instances. Before moving forward, we must understand aspect ratio calculations, because if we don't adjust for aspect ratio, the positions of our instances will distort when switching between landscape, portrait, or custom resolutions. The aspect ratio of a screen or composition is the relationship between its width and height, expressed as a fraction or ratio. For example, a standard 16.9 resolution, 1920 x 1080, has an aspect ratio of 16.9, meaning for every 16 horizontal units, there are 9 vertical units. Then, in blob tracking, the output coordinates are normalized UV values. These values are independent of pixel dimensions, but their proportions change if the screen aspect ratio changes. When working with any resolution other than a perfect square, the y-axis needs to be scaled to maintain the correct proportions. For example, let's switch our composition to a 16.9 aspect ratio. First, you'll notice that the instances have shifted and no longer align with the blobs. This happens because we need to apply a calculation to the height to correct this issue. The simplest formula to do this is dividing height by width that will give us this number, 0.5625. Now we can use this value to change the v coordinate and height by multiplying it by 0.5625 in the second math chop. This compresses the vertical space accordingly, ensuring that instances maintain the correct proportions. Now, if we switch to another well-known aspect ratio in portrait mode, such as 9:16, we follow the same calculation and apply it in the same way to the v coordinate and height. For example, let's change the resolution to 1080 corner 1920. We already know that dividing height by width gives us 1.777. By using this value in the math chop, we correct the aspect ratio issue, ensuring the instances remain properly aligned. You can also map these values from the constant, so the calculation happens automatically whenever you choose any resolution. Here, I'm dividing the height by the width, just as we did manually. Now that we've aligned the instances, let's see how to position text using blob tracking data. In top operators like the text top, we use absolute pixel coordinates instead of UV values. So if our resolution is a 1080 x 1080, the x and y positions range from 0 to 1080. That means if we want something right in the center, we set x equals 540 pixels and y equals 540 pixels. Unlike UV coordinates, which always stay proportional, absolute positioning depends on the screen size. So let me explain this next network, which will allow us to convert the relative UV coordinates into absolute XY coordinates. You can also use this as a template for future projects. Here I have created 3 select operators to separate the values I need. In this case, the first one selects the ID, the second one selects the U coordinate, and the third one selects the V coordinate. We leave the ID as it is. I added a null just for symmetry, but it's not necessary. The second and third select operators have a math operator connected, which we simply use to multiply the input value by the resolution we need. This approach makes handling aspect ratios much easier because we only need to multiply the values by the desired resolution. Since we are working in a horizontal layout, we multiply the U coordinate by the width and the V coordinate by the height. Finally, we use a merge operator to store all the values in a single operator. With rename, it's important to use specific names, text, X, and Y, because these are the ones that the text operator will look for. Finally, we convert this into a table and drag it into the specification DAT option. This ensures that the text appears in the same positions as the blobs. Now that everything is well explained, let's create the network for our project. A quick pause. If it's your first time on the channel, hi, I'm Okamarufu, and I share your obsession with learning TouchDesigner. I love this program, and I do my best to share everything I know to make learning easier for you. If you want to go even deeper, you can join nearly 3,000 people on my Patreon, where you'll get access to all my free VJ packs, complete project files, and exclusive components and plugins. I've also set up a fully organized shop with conceptual VJ packs, advanced plugins, and a lot more. Everything is neatly arranged in collections, so you can easily find exactly what you need. And if subscribing isn't your thing, no worries. You can still grab individual project files anytime, no strings attached. So if you're ready to take your visuals to the next level, create better projects, and support what I do, check out my Patreon. Chapter 2, Network. Remember, I'll now show you a screenshot of the network so you can copy it. Depending on its complexity, it might take more than one screenshot, and I'll include clear indications whenever necessary. Chapter 3, Parameters. All right, I'm going to explain how this network works while we review the parameters that best match the results we want to achieve. First, the constant is simply set up to define the width and height of my resolution. The trick to making this network fully parametric is as follows. Right-click on the value and select Copy Parameter. Then go to the Render top, right-click on the corresponding parameter, and choose Paste Bind. Now go up one level by clicking the home icon. Navigate to the project container. And bind the value there as well. Go back into the network and repeat the same process for height. I already have this set up, so let's move on. The keyboard operator is there just to reset the cache. When I switch to a different video or source, I want to reset the frozen background. To do this, simply reference the keyboard operator directly in this parameter. As for the noise operator, I honestly don't remember where I referenced it. However, I've created a free custom component called the Finder, which helps locate all references in a project. Just click on the operator, select Find Expressions, and in the From operator menu, you'll see all the operators that reference others. In this case, I found that the noise operator is linked to the opacity parameter in level 3. Remember, you can find this custom component in the free section of my Patreon. In the blob section, things are pretty simple. We have a select top that lets us drag in any source we want. Later, you'll see how useful it is to connect everything using select top. This select is connected to both a cache top and the main component, Blob Track top. The cache top is set up with prefill enabled and toggled off by default. With this pulse, we can refresh the cache every time we select a new source different from the current video. You can keep the cache size at 1, along with the step size. The Blob Track top has several parameters, but we mainly need to adjust 2. Minimum blob size, which sets the smallest detectable blob, and maximum blob size, which does the opposite. If both values are set to their extremes, the system will capture blobs of all possible sizes, but be careful. This can be very resource intensive. Finally, we use the threshold parameter to control the number of blobs visible on the screen. At the end of this section, we have a table date and a date to chop operator that converts them into a chop values. The network for 3D instances and text instances is the same as the one we covered earlier, so nothing is different here. I just recommend disabling the viewer for these nodes to save system resources. Before we continue, thank you all for watching and subscribing. Reaching over 15,000 subscribers in just 10 months has exceeded my expectations. Still, 77.1% of viewers haven't subscribed. If my videos help you, please hit subscribe. It really supports creating more high-quality TouchDesigner tutorials. Now, let's move to the SOP operator section. Here, I've simply created a rectangle SOP without modifying any parameters. The material is a constant mate, and all you need to do is drag it onto the geocomp to assign it as the material. To create the instances, this is identical to what we saw at the beginning. Make sure to enable instances. Drag this operator inside the geocomp and select the appropriate values, X and Y for positions, and height and width for the size of the rectangles. Now, let's dive into the post-processing network. The first part of this setup includes a couple of interesting tricks that are incredibly easy to apply. First, I've created a noise top. You can copy these parameters. And don't forget to animate the Translate Z in the Transform menu to add motion to the noise. Use the classic expression abstime.seconds divided by 15. And to finish, and to make sure the entire network has the same resolution, go to the Common tab and set the output resolution to parent panel size. In the composite top, I'm using the multiply blend mode. This allows the white rectangles from the instances to act as a mask for the noise, giving the blobs a textured look. For the displace top, you can try these values, but feel free to experiment with different settings. The select top here is pulling data from the Blob Track top. We've simply dragged this operator inside the select top to keep the network organized. Now, as you can see, the displace top creates a distortion effect based on the blobs, combined with the noise. This results in an effect that resembles a topographic scanner or something similar. Next, I'm going to mix these two signals, the output of the displace top and the same noise top from earlier. In this select top, I've just dragged in the result of the blobs with noise to maintain network organization. Then, I mix them in the composite top using the divide operation. We're almost done. Here we have the classic feedback network, where we'll simply adjust the opacity in the level top. Just go to the opacity parameter and set a value that looks interesting to you. Don't forget that the composite top, which blends the original signal with the feedback, is referenced inside the feedback top. Make sure you've dragged it into the operator. You can use either the A-top or over operation. Both work well. Next, we have another displace top, which creates a subtle distortion effect. To achieve this, we need to connect a noise top to the displace top. You can copy these exact parameters. Go to the Transform tab and animate it using the same expression as before. Again, don't forget to set parent panel size in the noise top to maintain consistency. Now, let's move on to the final blending. First, I've added a level top after the displace top because I only want to activate this distortion effect at certain moments. That's why I've referenced the noise top in the opacity parameter of the level top, so it follows the noise variations dynamically. The select top below is pulling in comp2, which is the final output of our network. Below that, I've added a text top. Also set the text resolution to parent panel size. In this text top, we'll receive values from the chop to operator we created earlier using chop operators. This ensures that all blob texts appear correctly in our composition. Finally, in the composite operator, set the blend mode to brightness. And we're done. Drag the composite top into the select top, and now we have the complete project ready to go. I hope you've successfully completed this tutorial. If you have any questions, feel free to ask in the comments or join the discussion.